Hi there, this is a video lecture introducing MOSFETs and specifically their physical operation. I'm using PowerPoint slides that were made available by the publisher, Oxford University Press, for the textbook by Sedra and Smith titled Microelectronic Circuits. This is the 6th edition and we're in Chapter 5. And in this chapter, so part of these slides will introduce the chapter. I won't be going through all of the slides from the chapter, obviously, in this presentation, but we'll get through at least a good portion of the physical operation slides. Okay, but first, let's just look at what is involved or included in this chapter. So in this chapter, we'll look at the physical structure of the MOSFET transistor, how it works. We'll then look at the voltage current characteristics of the MOSFET, how we can use a control voltage between two terminals to control current flowing through to the terminals. And then we'll look at how we can use such a transistor to make a useful amplifier, or how it can be used as a switch in a digital circuit. We'll revisit linearization, how we can generate or achieve linear amplification from a fundamentally nonlinear MOSFET transistor. And then we'll look at 3 standard topologies for how to wire up a transistor, be it a MOSFET in this chapter, and then in the next it'll be bipolar junction transistors, in such a way that we can achieve amplification with different properties. And these 3 different topologies of how we wire up a transistor lead to different characteristics that each are useful in certain contexts. And actually a practical amplifier that is made up of multiple amplifier stages will typically include a variety of these 3 different topologies, drawing on the strengths and distinctive features of each. And then lastly, we'll look at some practical circuits for MOSFET transistor amplifiers that we can construct with discrete components. So should be noted, this textbook is called Microelectronic Circuits. The focus of the textbook is ultimately to drive at creating integrated circuits. So a lot of the concepts are targeted toward solving challenges, problems, constraints that come with designing and building integrated circuits. In the course, and particularly in the lab exercises, everything we're going to build and interact with is going to be discrete, so we'll use discrete components. So although the textbook will drive at amplifier or transistor circuits that would ultimately be implemented as an integrated circuit, the course will not, and to boot, the textbook does have portions of each chapter that do address the discrete components, and we'll definitely focus our attention on those in the class. Alright, so far we've studied diodes. Now we're going to look at 3-terminal devices. I'm assuming if you're watching this, you have already had an introduction to transistors, so this is not completely new. Much of this is going to be a review in terms of at least the operation of a MOSFET, but probably the new part is the physical operation of a MOSFET. How do we get to that terminal characteristic that's known for a MOSFET based on the physical construction. Alright, so we're going to be controlling current through our drain here, the terminal labeled with ID, by controlling the voltage between the gate, VG, and the source, which is the terminal there tied up to +5 volts. Okay, what are the 2 major types of 3-terminal semiconductor devices? The first is the MOSFET, the metal oxide semiconductor field effect transistor, and the second is the bipolar junction transistor, or BJT. There are derivative devices that are also well known and well used within certain applications. The FET, just the field effect transistor, is in the MOSFET family. It is not as heavily used nowadays as it had been in the past, but it is still a legitimate device. Under the bipolar junction device family, there are IGBTs, insulated gate bipolar junction transistors. There are SCRs, silicon controlled rectifiers. There are thyristors, etc. But these are the two transistors that will be discussed in this textbook, and these will be the two types of transistors, that we will be interacting with through our lab activities and project at the end of the semester. Okay, why are MOSFETs more widely used? Well, they have a smaller size, they are easier to manufacture, they use less power, at least in a lot of the targeted applications that are discussed in this textbook. Current state-of-the-art, the VLSI, very large-scale integrated circuits, have upwards or over 2 billion transistors on a single IC. I think I've seen 2.8 or so. And it's considered, MOSFETs are considered preferable to BJT technology for many applications. So, but not all. So there are definitely, BJT is alive and well. You see them more in the power industry than you see them in the, certainly in the digital domain. In digital domain, digital electronics, CMOS, complementary MOSFET technologies, is by far the most dominant. And you will also see some mixed signal technology, so analog, digital type ICs will employ a mix sometimes of MOSFETs and bipolar junction transistor technology. Okay, enough on that for now. Okay, here's the structure of the MOSFET. And you notice that in the figure here, the title, it's an N-channel enhancement type MOSFET. So we haven't seen the term enhancement yet, but in general, there are enhancement and depletion type MOSFETs. Once we've studied how a MOSFET operates looking at the enhancement type MOSFET, it's not a far stretch to appreciate the principle of operation of a depletion MOSFET. However, enhancement is by far more heavily used, much more heavily used than the depletion mode type MOSFET, and so we won't actually talk about the depletion mode. Essentially, enhancement, I'll just tell you, enhancement mode means that the channel that will provide the conductivity between the drain and the source is not initially present when the device is not powered or when the gate does not have a voltage applied to it. You must enhance its conductivity by applying an electric field or potential between the gate and the source. But there are devices, depletion mode MOSFETs, that actually start out as having a channel, even without the application of a gate voltage, and then you can deplete them by applying the appropriate polarity of gate voltage. You can then turn off the channel. Okay, so again, we'll be looking at the enhancement mode devices. So the structure is basically, at least this type of a MOSFET structure, which is going to be used to explain the operation, has a uniform substrate. In this case, it's a P-type substrate because this is an N-channel MOSFET. And there are two wells, two N-type wells. These are labeled N+ because the plus indicates that they are heavily doped. So there are more impurities, more phosphorus impurities in the N material here than there are boron impurities in the P channel, or in the P substrate area here. There's a silicon dioxide insulation layer above this area that's denoted as the channel region. It separates this metal, this electrode that is the gate, from the channel. And so you're familiar with how no current flows into the gate of a MOSFET, at least not statically, not in DC, and that's because there is this insulator between the gate and the rest of the device. Okay, notice that also that the drain and source initially are completely symmetric, and so you could call either one of these the source and the drain at this point, because there is a fourth terminal here called the body or the substrate, which has not yet been connected to either the source or drain. Eventually it gets connected over to the source, well, to the left side here, and then that's when we call this well, we associate that with being the source because it is the one that is tied electrically to the body. Okay, so in other words, the source terminal always has 0 volts between it and the body electrode down here. And if this is a discrete device, like we use in the lab, the body and the source are tied together, internal, and we only have 3 terminals coming out from the device: the source, the gate, and the drain. Okay, I think I've mentioned all of these already, so let's move on. All right, the name MOSFET's derived from its physical structure. However, many MOSFETs these days don't actually use any metal. They use instead of polysilicon. So the gate electrode there that was traditionally metal now uses what is known as polysilicon, but the name has stuck. Okay, it doesn't have any bearing on the actual operation of or modeling of the MOSFET. We'll often call the MOSFET, just refer to it as a FET. I've never actually seen it called an IG FET, but I guess some people call it that. All right, it is a compound of 2 p-n junctions. However, these 2 junctions remain in the reverse biased at all times. Now, there's some exception to that on the body or drain to source diode, and we'll talk about that later. But typically in the MOSFET operation, as we think of it traditionally, that diode remains off. All right, so now let's look at the operation of the MOSFET when there is 0 gate voltage. Here we see the 2 intrinsic diodes that are between the source well and the body, and the drain well and the body. Okay. Now what happens if the source and the drain are grounded and a positive voltage is applied to the gate? So the first thing is that positive charge is going to build up on the gate electrode because the gate is now at a positive potential relative to the rest of the MOSFET. Secondly, this buildup of positive charge at the gate causes free holes to be repelled from the region of P-type substrate under the gate. Now recall that in the P material we have these acceptor atoms, right? These boron atoms that have a vacancy down in their valence band. It's charge neutral initially, but they are very willing to receive an electron. So if they borrow an electron from their neighbor and that electron moves into that hole, that electron now leaves a hole behind it, which then gives the sense that positive charges are actually moving. Now, when an electron moves in to fill a hole up here in the in what will be the channel region eventually, it uncovers a negative, a bound, I should say, a negative charge, right? An electron goes in and fills that hole, and now that electron is part of this ionized boron atom, and so we have a net negative charge in this region. Okay, so those negative charges now have filled up all of the valence band. So if you recall, the valence band for the P substrate has these vacancies. These electrons have come in and filled those vacancies, so there's no more spots, so to speak, for electrons to fill up any of the valence band. So now what will happen is that because of the positive charge or the positive voltage applied at the gate and the subsequent positive charges that have accumulated there, they will attract electrons. The electrons are going to come from the heavily doped N regions at the source and the drain. Lots of free electrons up in the conduction band, and they now move out under the influence of the electric field from the gate. They move out into this channel region, and they can move out there and remain in the conduction band because the valence band has been completely filled, or its electron, those holes have been completely filled with electrons. So we now create what will be known as a N channel. It's an induced channel. Okay. All right, 5. Once a sufficient number of these electrons accumulate, an N region is created. So we now have this solid path going between the two N+ wells. This provides a path for current to flow between the drain and the source, and it is called or known also as an inversion layer because we effectively have inverted what was intrinsically a P-type region into an N-type region. Okay, now let's look at some terms that will be seen. So we have threshold voltage, field effect, overdrive voltage, and oxide capacitance. Threshold voltage you would have seen before when we first introduced MOSFET in a previous course. Recall that this is distinct from the thermal voltage, which shows up in the Shockley equation for diodes, and it will show up again when we look at BJTs. The subscript little t is used in the textbook for the threshold voltage to distinguish it from capital T, which is the thermal voltage. The threshold voltage is the minimum voltage that's required in order to induce that inversion layer to create that channel. For integrated circuit transistors, this is typically between 0.3 and 0.6. For discrete devices, it can be much higher. You've noted, in the lab from working with discrete transistors, it can be on the order of a volt. It can be up to a couple volts for larger devices, particularly power transistors. Field effect comes from the fact that when we apply positive VGS to the gate and source, we create an electric or induce an electric field between the gate and the channel, and the conductivity of the channel is modulated by that electric field. It's increased as we increase the strength of that electric field. The overdrive voltage, VOV, is just defined as the gate to source voltage minus the threshold voltage. So it's how much voltage we're applying between the gate and source that's in excess of the minimum that's needed for creating that inversion layer. And lastly, the oxide capacitance, COX, is actually a capacitance per unit area. So if you recall from university physics, the capacitance formula for a parallel plate capacitor is the permittivity of the dielectric times the area of the plates divided by the separation between the plates, or the thickness of the dielectric, if you will, that's between the plates. Here you see the permittivity and you see the thickness, which is T sub OX, but you don't see the area because this is given as capacitance per unit area, and this shows up a lot in the equations that follow. Okay, so now we're ready to start thinking about how we can quantify or characterize the current that's going to flow through this induced channel. So the approach we're going to take is to think about charge. First, think about charge that is contained within the channel, and then we're going to think about characterizing the velocity at which charge flows in that channel. And if we know charge and we know velocity, then, or I should say charge per unit length times velocity, which would be length or meters, per second. The product of those two would be coulombs per second. So that's kind of the big idea of how we're going to ultimately get to a current flow. Okay, so let's start with looking at the charge that is in the channel, and that's this equation 5.2 here. So first we need capacitance. Right, charge is equal to capacitance times voltage. Right, our capacitance here is actually COX, which is the capacitance per unit area, times the area of our parallel plate capacitor. The area is the width of our channel times the length of our channel. So that's why the charge that's contained in the channel is equal to COX times W times L, that is the capacitance in farad, times the overdrive voltage. Now it's just the overdrive voltage and not all of VGS, remember, because it takes V threshold volts to induce that inversion layer, that induced channel, right? So only the overdrive portion of VGS will participate in actually bringing charge into that now inverted or induced channel. Okay, so total charge in the channel is COX times channel width times channel length times the overdrive voltage. And we see that as the overdrive voltage increases, so does the charge in the channel increase proportionally. So this now is an equation that describes what I said in words in the last slide. Okay, that we can get to the channel current if we know the charge in the channel per unit length, okay, per unit length times the velocity of the charge in meters per second. So we have coulombs per meter times meter per second. And when we take the product of that, we end up with coulombs per second, okay? So let's see, I think there's some more slides. Well, I think they add extra slides in this presentation. Let me just talk through this equation here and we'll be done with it, because I think it's pretty straightforward to understand it. Okay, so the term on the left comes straight from what we just looked at, the calculation of charge, which is just capacitance times voltage. But in this case, we've divided by L because we're interested in capacitance per unit length. Okay, on the right, we have charge or electron drift velocity, okay, which would be meters per second, and that comes about from the product of our electron mobility, mu sub n, times the electric field. Okay, so mu sub n we've seen before when we were looking at the p-n junction. This is a process parameter. So it's the electron mobility is different in n-type material versus p-type material, and it's going to differ based on the concentration of the impurities, right? If you put twice as many phosphorus atoms in your n-type material, you're going to have a different electron mobility. So it's electron mobility times the electric field. The electric field here is expressed as VDS, the total voltage between the two ends of the channel, divided by the length. Now this assumes, right, that we have a voltage between VDS. On the other hand, we are assuming that, as we saw on the previous slide, and as we see now on the left term of this equation, that we're assuming that the effective overdrive voltage at every point along the channel is VOV. Okay? In reality, if the drain's voltage is a little bit higher than the source voltage, then the effective overdrive voltage at the drain end is going to be a little less than the overdrive voltage at the source end. But because of the small VDS approximation here, we're able to ignore that, and we can calculate the total, the charge per unit length as being constant along the channel, because we're assuming this constant VOV along the channel. And that's okay for small VDS, and this is small VDS relative to the threshold voltage. Okay, so let's move on here. This is just working through what I've talked about here. Here's another slide that kind of takes it in steps. Here's the electron drift velocity is the mobility times the electric field. Electric field here is going to be VDS, voltage, divided by the channel length L. Okay, let me move on here. Okay, so this is kind of the summary slide. For small VDS, we have this linear relationship between the drain current and the drain to source voltage. And the constant of proportionality is in the square brackets there, and we see that it's a function of the geometry of the channel, so width and length, the overdrive voltage which we supply, and then these process parameters which are the COX and the electron mobility in the N channel. We can actually define a channel resistance by doing VDS over ID, and we see there that it's 1 over mu n COX W over L times VOV. So we apply a bigger overdrive voltage, we're going to get a smaller RDS. Now, as you know probably already from working with real devices, there's a limit to how low this can go. So just by adding more VOV, you don't just keep reducing RDS. There is a limit to it, and your data sheet will tell you what the typical on resistance is for a particular overdrive voltage. It'll actually even give you graphs usually of what RDS is as a function of overdrive voltage or VGS, and it tapers off. So it goes down as a function of VOV, but then it tapers out to a minimum because there are other resistances involved in the channel besides just the resistance that's due to available charge, if you will, that's in the channel. Okay, so here's a recap on RDS. It depends on 3 things. 1 is the process parameters, mu n times COX. 2 is the aspect ratio geometry of the transistor, and 3 is the overdrive voltage, which is what the user has control over. If we plot ID versus VGS, we see that it's a straight line. This is again for small VDS, right? Small VDS, and the slope increases for increasing overdrive voltages. The slope is 1 over RDS, so this increasing slope is indicating higher conductivity through the channel. Okay, so for small VDS, again, we can kind of treat the MOSFET as a linearly programmable resistor, okay, which does have some applications. Now, what happens when we look at a larger VDS, right? Obviously, to make this device useful, we're going to have to operate it with higher VDS, right? Well, we can no longer assume that the voltage across the channel from source to drain is constant, okay? And we see that here down in this last slide, or the last equation. The voltage between the gate and the drain is no longer just equal to the voltage between the gate and the source. Okay, I'm sorry. Is no longer equal to just VGS, because VDS now is significant. So let's go to the next slide because it shows a graph which just makes it more understandable because of the graphic. Okay, so the depth of the channel, we've said already, is proportional to the overdrive voltage. Right? Let's say that the source is grounded. Let's say VGS is equal to 1 volt, and so we have or let's say 2 volts here. So we have a channel that's of a particular depth here. Okay. Now let's say that the drain to source voltage is equal to 1 volt. Okay. So that means that over at this end here, the gate is at 2 volts, the drain is at 1 volt, and therefore the effective voltage is 1. Now I forgot to mention the overdrive voltage. So let's say that the gate to source is 2 volts. Let's say the overdrive voltage is a 1/2 volt. Okay, so that means that our effective overdrive here is 1.5 volts. But over here, our overdrive will be decreased by 1 volt, so it'll only be a 1/2 volt. So a 1/2 volt effective overdrive here, 1.5 volt effective overdrive at this end, that would imply that the channel depth at the left end is 3 times deeper than the channel depth at the right side, up at the drain. Okay, so previously for the small VDS approximation, we assumed that the effective overdrive voltage along the whole length of the channel was just VGS minus V threshold, and so we had a constant depth, and therefore our charge per unit length was constant along the whole length. Now we're going to see that's not the case. So let's go to the next slide here, and this will graphically help us arrive at a modification to our formula previously that we used for ultimately calculating current. What we're going to do is we're going to again look at how much charge is in the channel. Okay, so ultimately this is the expression we're going to end up with. But let's look at this top graph here. What we have is on the vertical we have voltage. Okay, so here over at the source, which is on the left side, we have a total gate to source voltage VGS. Here we'll say that it's let's say that it's 2 volts. Okay, and let's say that our threshold voltage here is let's say 0.8 volts. Okay, so we have 1.2 volts of overdrive right here. And then as we move over to the drain, we have a drain to source voltage. Now let's say that that's about, I shouldn't have picked numbers. What did I say? 0.8, so that's 1.2. Let's say this is 0.8 volts as well right here. Okay, 0.8 volts. So our overdrive voltage at this end is, what do we say, 1.2 minus 0.8, so about 0.4 volts. 0.4 volts overdrive here and 1.2 volts of overdrive here. So the depth of our channel is proportional to this distance here. This line, the blue line, is the voltage at the location X. Okay, X is our variable that indicates the position along the channel. Okay, and we go from 0 volts up to a voltage of VDS, or 0.8 volts, at the point that we reach the drain. All right, and the distance between this channel voltage Vx and our VGS minus threshold voltage here is the effective overdrive voltage at that point in the channel. Because this is a straight line, and ultimately we're going to be looking at to calculate the total charge in the channel, we can actually just calculate the average overdrive voltage and use that to calculate the charge, and that's what's done here. So here is the channel. The channel depth is going to be proportional to this area right here, this trapezoid. How do we calculate that area? Well, we can take the total area of this rectangle and then subtract this triangle, right? And that's what's done right here. That's why we do VOV, which is the total height minus 1/2 of VDS, and that's the effective overdrive voltage for our entire channel. So now let's look at this result graphically. What we have here is the drain current being plotted versus the drain to source voltage, and we have repeated down below this triode equation, which is what we just arrived at by replacing the once fixed VOV voltage coming from the small VDS assumption to now a VOV minus 1/2 VDS. And this, when plotted, gives rise to this initially linear looking curve, right, which is the region that we first looked at, the small VDS. But as we increase in VDS, moving to the right horizontally, the minus 1/2 VDS becomes non-negligible compared to VOV, and that produces this curve, this decreasing slope. At the point that VDS is equal to VOV, right here at this dashed line, the channel at the drain goes to a depth of 0. Okay, and we say that the channel is pinched off, and we're going to talk a little bit more about what that means here shortly. But for the moment, what we are claiming is that for VDS greater than VOV, the channel doesn't get any shorter. It just stays as this triangle with the 0 depth at the drain, and the conductivity of the channel does not increase any further. And so we end up with a saturated current, which is equal to this second expression down below, this saturation expression, which is now a function only of VOV, no longer a function of VDS. Okay. Now we're going to look at what actually happens in the saturation region, because it doesn't actually stay completely flat. It actually has a shallow slope, and this is called channel modulation. And you've maybe have seen this previously, but we'll look at some of the kind of the underlying physical reasons for it. Okay, but before we leave this slide, just to recap, the MOSFET has these two regions that we've looked at. One is the triode region. That's where we've spent most all of our time. That's triode region is where the channel is continuous from the source to the drain, albeit the channel is not of a consistent depth between the source and the drain. It actually will narrow as you approach the drain, but it never actually pinches off to a 0 depth, okay, until you get to a VDS of equal to VOV. All right, and then to the right of that is where the channel is pinched off, and with we say the transistor is in saturation, and now the current is no longer a function of VDS. Okay, so clearly this is not from the publishers. This is my little chicken scratching. So here we have on the left the source well and the drain well on the right, and I'm depicting here this channel, the induced channel, which has an initial depth on the left due to VOV, VGS minus the threshold voltage. And now I've exaggerated what actually happens on the right side. You see that I'm showing that the channel pinches off at a voltage or at a location X. If we say X is 0 here at the source and then X is equal to L over at the drain, it pinches off, it goes to 0 depth at a location X that is less than L. Now, like I said, this is exaggerated. I've made this probably a lot longer than it actually is. So what happens when the voltage VDS becomes greater than the overdrive voltage? Well, what will actually happen is that there is going to be a region near the drain where there is actually complete depletion. Okay, there is no channel. And in that region, there is going to be an electric field that is going to be induced or set up, and it's pointing to the left because the drain is positive with respect to the source. Now let's imagine for a moment that the drain is at 10 volts and the source is at 0 volts. And maybe the overdrive voltage for this device is, let's just say 1 volt. Okay, so at this position here, this location X, where the channel goes to a 0 depth, we would have an overdrive voltage there, VOV, effective VOV, of 0, right? We have 0 VOV there. Let's say the gate voltage is set to 2 volts, okay? So over here at the left, I have 2 volts minus 1 volt for a threshold voltage, and that gives me a 1 volt overdrive, right? And at this point here, I'm going to say that this voltage X must be at 1 volt. Okay, the voltage of the channel at this point is 1 volt. The gate is still at 2 volts. So the difference between the two is 1 volt, which is the overdrive voltage. So my channel has a depth of 0. All right. Now, as I've walked from an X of 0 up to an X of whatever that value is, I have traversed 1 volt. I was at 0 volts at the source, and now I'm up to 1 volt here. But yet by the time I get to the drain I said was at 10 volts. So that means that in this distance here, depicted by the orange arrow, I have a 9 volt difference. All right, so I'm dropping 1 volt across my channel, and then 9 volts I am now dropping in this depleted region. Now, if this region is very small, which it will be, the electric field in that region is going to be very large, because the electric field is voltage divided by length. Okay, so I've got 9 volts divided by whatever that length is. And what will happen in that region is that the electrons that are in this channel and that are mobile will be moving to the right, right? Because I have an overall, remember I have a 1 volt potential here between the source and up to this point. So there's going to be an acceleration, a velocity to these electrons moving to the right. They get to this point here, and suddenly now they go from having a relatively small electric field, 1 volt spread over the length of most of this channel, right? Small electric field. Now suddenly they have this 9 volts divided by this very small distance, right? And so they'll have a very strong electric field. Those electrons, once they get near this electric field here, will get just swept, accelerated across this gap, right? But as they move across that gap, they are also losing energy, because as electrons, they're moving from a more negative potential now to a positive potential that is 9 volts more positive. Right, so that's this analogous to positive charges dropping through a potential difference. So although electrons will flow in this region, it's a very dissipative process. They actually will be giving up a lot of energy, and of course this is analogous, or this corresponds to the transistor in its saturated region behaving like a constant current source. Right, and you can put whatever voltage you want across the current source, and it will still give you the same current. Well, that's going to be essentially the same case here. The net voltage between the left side here where the source or where the channel meets the source and is at a 0 potential, and over here where it gets pinched off, which is basically 1 volt from the source, you know, that electric field is going to be pretty constant. It will only change if this channel length changes, right? Why would this channel length change? Well, if we continue increasing the drain voltage, there will be a slight modulation of this channel. It will shorten a little bit, okay? If it shortens a little bit, then now we have the same potential difference, 0 volt to 1 volt, but now it's divided by a slightly shorter distance. So if it's a slightly shorter distance, same 1 volt divided by a slightly shorter distance will produce a slightly greater electric field in this channel. That slightly increased electric field will produce a slightly increased current, right, through this channel. And so that's what leads to, I don't know if I have a slide for this, but let's click through here and see if we see one. Sooner or later we will see one. I get to this much later. There we go. There we go. Okay. So here you see the saturation region with a highly exaggerated channel modulation going on in this region here. You may have seen this introduced previously, not from a physical or operational perspective, but rather just from a kind of terminal perspective of how do we describe current in the saturation region. And we defined what's called an early voltage. I don't know if it's called out here, but this voltage here, minus VA, which is sometimes also depicted, well, not sometimes, it is also referred to as 1 over lambda. This parameter is useful for describing what happens related to the channel length modulation as you increase the VDS voltage. So we can actually model the modulation and the change in current in the saturation region if we know this early voltage. Let me see if I have a expression for it. If I go back to a last slide, and then we'll stop here. I know I've seen it. Here we go. Okay, right here. So this is kind of our recap. So down here, this last equation here, we see that in the case where VDS is greater, much greater than the overdrive voltage in this case, we have 1/2. This is our Kn here, process, our MOSFET transconductance coefficient, times the overdrive voltage squared, so it's VGS minus threshold voltage quantity squared. And then here we see 1 plus this term here, lambda times VDS, or you'll see it sometimes as VDS over VA, the early voltage. This is the way that we can modify our basic saturation equation here to include this effect of channel length modulation. Okay, so let's recap, and we'll end this talk. For small VDS, we can assume that the VOV, the overdrive voltage, along the whole length of the channel is constant, and so we have basically a current that is just proportional to VDS. The channel acts as a programmable resistor. We can program it with a resistance that's inverse to VOV. When VOV or VDS is less than VOV, but not much less than VOV, we now have to take into account that the effective overdrive voltage, as we move to the right along the channel from the source to drain, actually decreases, and it decreases on average, it decreases such that the average VOV across the whole length of the channel is VOV minus 1/2 VDS, and this leads to a reduction in current as we go up to higher, well, a reduction in slope of current as we go up in VDS. At the point that VDS is equal to or greater than VOV, that equation now ceases to increase. The ID ceases to increase, and we have a fixed ID that's a function only of the overdrive voltage. And then if we are going to be working in an application where the VDS can become significantly higher than VOV, then we can include the channel length modulation by either having the this term lambda, or equivalently 1 over the early voltage. Okay, so I think this concludes our presentation of the physical operation of a MOSFET, and from this point on we'll be looking at the terminal characteristics using really just these equations to help us characterize the behavior of the transistor in a circuit. And from there we'll then look at how we can linearize it and then use it as a device that allows us to achieve amplification.